Hey everybody, welcome to yet another video of the FY6 classroom. In this video, we're going to review everything that you need to know in regards to one-dimensional motion. If this video is helpful to you, go ahead and hit that like button. And if you want to see more videos, make sure to hit that subscribe button. But right now I need you to go get something so you can take notes because we're going to go over everything that you need to learn about one-dimensional motion. Well, when we're talking about one-dimensional motion, what do I mean by that? Well, one-dimensional motion is when an object is only moving in one direction at a time, such as a runner moving forwards or a rocket ship going upwards. It's only moving in one dimension. We live in a three-dimensional world where there's the dimension of forward and backwards, there's the dimension of left and right, and there's also the dimension of up and down. That's where we get our three dimensions or 3D from. But when we're talking about one-dimensional motion, we're only talking about an object moving in one of those dimensions at a time. So it can be horizontal or it can be vertical, but it can't be both of them at the same time. So when we're going through this, there's going to be a few things that we're going to cover, and I want to go ahead and introduce them to you. The first thing we're going to talk about is velocity. And we're going to go really in depth about it, how to calculate it, what does velocity even mean. We're also going to talk about acceleration. And we're also going to go over velocity and acceleration in the forms of motion graphs. And not only that, we're going to talk about how velocity and acceleration are affected when things are in free fall. But before we get into these things, there's another topic that we need to cover, and that is the topic of position. So position is basically representing where you are. And how do we represent where we are? Well, we first need to decide what our reference point is, and then we can tell our position based off of that reference point. If you're trying to tell your friend where you are, you usually say, I'm at the store. The store would be the reference point. Or I'm next to the fountain at the park. You're giving a reference point to your location. So for us to tell the position of something, we need to have some sort of reference point. And for us, we're typically going to use a number line or some sort of XY coordinate plane as our reference point. So we can use the number line or some sort of grid to denote our location in a certain area. So you first need to always define an origin. What's your zero position? You know, on a number line, there's a 0 point. On an XY coordinate, there's an origin. That's where the X and Y cross. And then you're going to decide what your zero position is, and then you go from there. And then the next thing you want to do is decide what is the positive direction. And there are some typical direction rules that we got to follow to make sure that we are all on the same page, because these direction rules can just be made up by anyone at any time. But for all of us to make sure we're working together in the right way, we all need to start following these same direction rules. So the first rule that we're going to follow is that right and up, we're going to call those positive directions. We're going to denote that with a positive number. So if anything is moving to the right or it's moving upwards, we're going to give that number that represents the magnitude a positive sign. The next thing you need to know, well, it would be the opposite. Anything that's moving left or down is going to be considered a negative direction. So anything that's moving to the left or moving downwards, we're going to give that a negative sign for the number. It doesn't mean anything bad, it's just showing us which direction it's moving, to the left or downwards. And also another thing that you need to know, we typically say the ground or the floor is considered to be your zero or your origin if we're talking about something moving vertically. So ground or floor, 0, left and down is negative, right and up is positive. So with all of that said, let's start talking about speed and velocity. All right, so speed is basically the magnitude that represents how fast you're going, and you probably already knew that. Now, the technical definition of speed is the ratio for the distance you traveled and the time it took you to travel that distance. If we were to put it mathematically, speed is distance divided by time, and that's how you would, figure out how fast you're going. How much distance did you cover, and how much time did it take you to cover that distance? Now, velocity is very similar, but it is different. Velocity is the magnitude, how fast you're going, and the direction that you were going. So that direction is important with velocity. Speed doesn't have a direction, but velocity does. And the technical definition for velocity is the ratio of displacement and the time it took you to create that displacement. So speed deals with distance, velocity deals with displacement divided by time. And there is a difference between those, and we need to make sure that we know the difference between those two. Now, typically in physics, we will use velocity. Sometimes you might ask for speed. Sometimes these can even be used interchangeably, but we are typically going to be dealing with velocity. Now let's talk a little bit more about speed. Now, a car's speedometer tells you how fast you're going, but it doesn't tell you the direction that you're going. For you to figure out which direction you're going, you need some sort of compass along with the speedometer, or you need to rely on some sort of street signs or something, signs saying you're going north, and you combine that with your speedometer, you can get your velocity. But the speedometer doesn't tell you the direction, just tells you how fast you're going. Now, you can measure speed in all sorts of different ways, but it's always going to be some form of distance divided by time. So a couple examples of that would be miles per hour, or it could be kilometers an hour. Those are the two typical ways in the world that we measure speed in a vehicle. But you can also measure it in meters per second. And I put meters per second in yellow there is because typically in physics, all of our speed measurements will be in meters per second. That's our typical SI units for speed. Feet per second, that's another way to measure speed. Now, all quantities for speed are going to be positive because there's no sign to tell you which direction the object is moving. It's just a scalar quantity, so it doesn't tell us the direction. So we're just going to go ahead and say that it's all positive, and you can never get a negative speed. And let's go into velocity now. Velocity is the combination of speed and direction. And you represent the direction with the sign in front of the number. And like we've already said, positive is upwards or to the right, negative is downwards or to the left. And once again, you can measure velocity in many different ways, but it's always going to be some form of displacement divided by time. And there are multiple examples, but you're going to notice they're all the same. All of the ways that you measure speed and velocity are the same. Miles per hour, kilometers an hour, meters per second, feet per second. Once again, we're going to typically use meters per second to measure velocity. So we measure velocity the same, but the difference is the sign we put in front of the number. We can tell if the object is moving in the positive direction or the negative direction by putting a positive sign or a negative sign in front of the number. And that way we know which way the object is moving, and that's the extra information you get from velocity when you compare it to speed. Which way is the object moving? And now that we have speed and velocity under our belt and we understand what's going on, let's talk about acceleration. And a lot of people get confused with acceleration, but acceleration is basically the change in the object's velocity. And acceleration is a vector because it's made up of velocity, and velocity is a vector, so therefore acceleration would be a vector. Now, acceleration can be a change in the object's speed, so it could be speeding up or slowing down, or it can be a change in the object's direction. So if it's turning or going around a curve, the object is considered to be accelerating then too, because it's the change in velocity. And velocity is two things, speed and direction. If you're changing either one of those, you have an acceleration. For us to calculate acceleration, it's the change in velocity divided by time. So if you start off moving slowly, then faster and faster, you're considered to be accelerating, speeding up. Now, if you're moving fast and then you're slowing down, you're accelerating in the opposite direction of your motion. So we sometimes call that deceleration or negative acceleration. And we're going to have a few examples of that here in a minute. So if you're moving at a constant speed, but you're changing the direction, so you're going around a turn, you're going to be accelerating. Now let's go into a few examples of acceleration and velocity. And we got this car over here, and it's got a velocity going to the right, which is the positive direction, and it also has an acceleration going to the right, which is also a positive direction. So what all is actually happening here? Well, in this situation, the car is speeding up, and it's speeding up in the positive direction. So the velocity is to the right, and its acceleration is to the right also, which means its velocity is increasing, and it's speeding up, going faster and faster and faster to the right, and it's going in the positive direction, which is to the right. Now let's look at another example here where the velocity is going to the right and the acceleration is going to the left. Well, what's happening here? Well, it's moving to the right. It is actually moving in the positive direction, but the acceleration is basically going the opposite way, which means the velocity is going to be getting smaller and smaller. So what does that mean? Well, the car is moving in the positive direction, but it's slowing down in the negative direction. That negative acceleration is causing it to slow down, but the actual motion of the car is still positive. Let's look at another example. Here we got our velocity going to the left and the acceleration going to the left as well. So what does that mean? Well, the velocity and acceleration are both in the same direction, so that means the car is speeding up, but it's speeding up in the negative direction. So its speed is increasing, but that negative sign there is just telling us it's moving to the left. And lastly, we got the velocity going to the left and the acceleration going to the right. So what's happening here? Well, the car is actually moving in the negative direction, but it's slowing down in the positive direction. So I want you to pick up a pattern here. If the acceleration and the velocity are in the same direction, like the two on the left over here, that means the car is going to be speeding up. And if you look at the two on the right, you notice the acceleration and the velocity are in opposite directions. That means the car is going to be slowing down. And also you notice the velocity vector tells you which direction the car is moving. The acceleration vector does not tell you which direction the car is moving, it just tells you in which direction the velocity is changing. Now let's talk a little bit about calculations. We're not going to actually do any calculations, but we just need to kind of go over a few formulas to make sure that we understand that they are there and that we will be using them. So there's going to be many formulas that you can use, but we need to talk about the variables in the formulas before I throw them out there. So the first variable is the letter D for displacement, and the units for displacement are in meters. So we measure displacement in meters. We'll use the letter D in our equations to talk about displacement. T is for time. Units would be seconds. So anytime you see the letter T, we're measuring time, and the SI units would be seconds. The other thing is going to be velocity with the letter V, and the units will be meters per second, like we talked about in the earlier slides. Now there's two different velocities that we're going to use a lot. We have VF, which is the final velocity, and we have VI, which is the initial velocity. So if there's some sort of acceleration going on, that means that the velocity is changing. Well, VF is going to be what was the velocity at the end, and VI is what is the velocity at the beginning. You might even sometimes see V0, and that's the same as initial velocity. So don't get confused if you see those. They mean the same thing. It's just two different ways to write it. And the last variable we're going to talk about is acceleration. We use the letter A to talk about acceleration, and the units for that are meters per second squared. So we have these equations that we use that are called the kinematic equations, and these are used to describe the motion of objects. So let me just kind of throw them out there at you really quick. You got your typical velocity equals d over t, which is displacement over time. We've actually already talked about that one. And the next one we've actually talked about as well, but I'm just going to expand it a little bit. We have acceleration is the change in velocity divided by the time. And you can also write that as the final velocity minus the initial velocity divided by time. It's two different ways to write the acceleration formula, so keep that in mind. And then we can rearrange it if we wanted to find the final velocity. We would have VI plus A times T, and that would be the final velocity. It's just basically the rearranged version of the acceleration equation up above it. And we have another equation here, displacement equals VIT plus 1/2 AT squared. This is a good equation depending on what variables you have. And then the last one, VF squared equals VI squared plus 2AD. This involves the final velocity equals the initial velocity, square both of those, and then you add 2 times acceleration times displacement. and you can get some other information. You can calculate different variables of the object's motion using these equations, and these are called the kinematic equations. Very, very good things to know. Now let's start talking about motion graphs. Well, what do motion graphs do? So motion graphs are used to show the motion of an object in some sort of graphical form. So we're going to have a graph, and we're going to be able to look at that graph and figure out what kind of motion is happening here. And we're going to focus on 3 different types of graphs. There's going to be position versus time graphs, velocity versus time graphs, and acceleration versus time graphs. And we're going to look at each one of those and figure out how an object is moving based off of those graphs. So the first one we're going to talk about is the position versus time graph. And this shows the position of an object as time is going by. And you can see over here on the right we have a position versus time graph. And on the y-axis we have our position, and time is on the x-axis, okay? If you remember back in your math classes, you learned how to calculate slope, which is rise over run. So that principle is going to be very useful when you're looking at a position versus time graph because it gives you a lot of really good information. Now on a position versus time graph, the rise is the change in position and the run is the time. So if you were to calculate the rise over the run, you're finding out the change in position divided by the time, which your change in position is displacement. So you have displacement divided by time, which is velocity. So when you find the slope of a line on a position versus time graph, you've actually found the velocity. And that makes sense because if the position is changing, you've had some sort of displacement. You're not where you were before, so there's been a displacement or a change in position. And that means that your slope is equal to the velocity of the object. That's going to be super useful, and you can calculate how fast something is moving by calculating the slope on a position versus time graph. So let's look at a few examples of position versus time graphs. We're going to start up here at the top left. What is happening? What kind of motion is going on here? Well, it's just a flat line, and remember, position is the y-axis. There's never a change in position in that whole thing. It's like you're standing still. Your position never changes, so that means, well, you're not moving, okay? Now let's look at this graph over here. That shows that you are moving and you're going from some position and then you go to 0 and then you start going in the negatives, okay? So you started off in the positives and you were going backwards. It's like you were moving in the negative direction. And because that slope doesn't change at all, there's the same slope the whole time. That means you're moving at some velocity, and that velocity didn't change either. Since the slope stayed the same, the velocity stayed the same. So therefore, we're going to say that that was a constant negative velocity. That's what was happening there. Now let's look at this one over here. You started off at 0, and then you were moving in the positive direction. The slope never changed at all the whole time. So what does that mean? Well, you had a constant positive velocity, and that's because the slope was in the positive direction. In the example before, the slope was going downwards, which is a negative slope, means you got a negative velocity. The third one here, we got a constant positive velocity because it's an upward slope, so a positive slope, and the slope never changes the whole time. It stays the same. Now let's throw a little bit of a curveball at you here. What's going on here? Well, we have a change in position as time goes by. You're not staying in the same spot, so you're moving, but there's not a steady slope the whole time. It's like it gets steeper and steeper as time goes by. So what does that mean? Well, if the slope is getting steeper, that means you're going faster. And that means if you're going faster and faster and faster, you're accelerating. So this shows acceleration on a position versus time graph. And since it's accelerating upwards, that's a positive acceleration. So this shows constant positive acceleration. Keep in mind, if you're looking at a position versus time graph and there's any sort of curve on it, there is an acceleration going on there. Now let's look at velocity versus time graphs, okay? So a velocity versus time graph just shows the velocity of an object as time is going by. So how is the velocity being affected over time? Now on this one, the y-axis is velocity and the x-axis is time. And once again, the slope is going to be very important, calculating that rise over run. And on this one, the rise is the change in velocity, and the run is going to be, once again, time. So what does that mean? Rise over run is equal to the change in velocity divided by time, and that's the equation for acceleration. So if you find the slope on a velocity versus time graph, you found the acceleration. And if the velocity is changing, there's an acceleration. So if there is some sort of slope, that means the velocity is changing. Therefore, we have acceleration of an object. Now, another thing that's very interesting on a velocity versus time graph, and you want to keep this in mind, the area between the line and the x-axis actually tells you the displacement. So if you can find that area underneath, you found out the displacement of the object. Let's talk about some of this. Let's go over a few examples. Let's look at this first one here. You got a velocity on the x-axis, which is 0. So that means that there is 0 velocity, and you notice it doesn't speed up, it doesn't slow down, it doesn't, do anything. So what does that mean? Well, that means the object is not moving. There's no motion going on. Now let's look at this example here. Here you got a flat line underneath the x-axis, so that means there's a negative velocity, right? And the velocity doesn't go up or down, it stays constant. So that means you have a constant negative velocity. It's like you're walking backwards at a steady pace is basically what's going on there. Now let's look at this graph right here. So you started off with a really high velocity, and then you went to 0, and then you started getting a very negative velocity. It's like you were going faster and faster backwards. So the first part, you were actually slowing down because you had a really high velocity, and then you went and reached 0. So you actually came to a stop for a moment. And then the next part, you're actually speeding up, believe it or not. So you start off slowing down, now you're speeding up. It's because you were at 0, and now you're further away from 0 meters per second in your velocity. So you started at some high velocity, slowed down to 0, and then when you hit 0, you started speeding up backwards. So what's happening here? Well, there's also a slope here, so that means there's a change in velocity, and a change in velocity is acceleration, and the slope is going downwards, so that means that's a negative acceleration. So what we have here is constant negative acceleration. Let's go to an easy one real quick. We got a flat line above the x-axis, so what does that mean? Well, the velocity is not changing, so that means the velocity is constant, and it's in the positive side of the graph, so that's a constant positive velocity. But let's talk about that displacement thing. So remember, the area underneath the line, so between the line and the x-axis, that's your displacement. In this case, it's a rectangle, so if you find the area of that rectangle, you found the displacement, and you would figure out the length by using time and the height by using the velocity. Very simple calculation, just a little bit of geometry there. Let's look at this example right here. So what's happening here? You start off with a 0 velocity, and then you went up to a higher velocity. So you're speeding up, which means you're accelerating, and it's upwards, so that's the positive direction. Therefore, you have constant positive acceleration. And once again, that area underneath shows the displacement. So in this case, it's a triangle. So you figure out the area of that triangle, then you found the displacement of the object. Let's do one more example here. So what's happening here? You have a very large negative velocity, and then it goes and approaches 0, and then it goes to a very high positive velocity. So the first part, you're slowing down. You're slowing down because you're approaching 0 meters per second. It's like you had a high velocity, and then you approach 0, and when you hit 0, you stopped. That's on the x-axis, and then you sped up in the positive direction of the velocity. And since the slope is going upwards the whole time, that shows a positive acceleration. So what we have here is a constant positive acceleration. Now the last type of graph we're going to talk about is the acceleration versus time graphs. And these graphs are really not as useful as the other ones, but they are there and we need to know them. They're not going to be used very often, but you notice that the acceleration is on the y-axis and the time is on the x-axis. And once again, You can find the slope using the rise over the run. And so we have a change in acceleration as the rise. We have time as the run once again. So you have rise over run equals change in acceleration over time. And we actually never talked about what a change in acceleration is. And the reason we didn't talk about it is because it's never used. If the acceleration is changing, we're going to call that the jerk. So if you have a slope on an acceleration versus time graph, you could calculate the jerk by finding the slope on the graph. But like I said, you'll probably never use that, and these graphs are really not that helpful. But let's just go over 3 examples real quick. What would no acceleration look like on an acceleration versus time graph? Well, it would look like this, just a flat line on the 0. It doesn't tell us if the object is not moving. It doesn't tell us if it's moving at a constant velocity. All we can tell is that there is no acceleration, which means there's no change in the velocity. We can't tell anything else from that graph. So let's show what a positive acceleration would look like. Well, it would look like a flat line on the positive side of the graph. Now, one other thing that is useful for us to know is that the area underneath the line is equal to the change in velocity. So you can figure out how much the velocity has changed by calculating that area, but you can't actually figure out what the initial and final velocities were. You can only figure out how much it changed. And then lastly, let's find the negative acceleration. What would that look like? Well, it would look like a flat line, just like that. Now, once again, these graphs don't give us a lot of information, and they don't tell us which direction the object is moving. It doesn't tell us the velocity. It doesn't tell us the displacement. There's not a lot of great information on these. We would probably have to convert this to a velocity versus time graph and then to a position versus time graph maybe. But they are there. You might have some sort of moment where you need to look at an acceleration versus time graph, but they're not packed full of great information typically. But finally, let's talk about free fall. And what do I mean by free fall? Well, free fall is whenever an object is only under the influence of gravity. So gravity is the only thing acting on it, and it's just falling through the air. I'm not talking about a rocket being propelled or anything. It's just an object falling through the air. We call that being in free fall. So here's a little diagram on the right over here showing an object starting off with 0 meters per second at the top, and then you can see the velocity is changing as it's falling, and you can see the time, the different times as it goes. So when an object is falling towards the earth, its speed is increasing, which means it's accelerating. You can see that in the diagram over there on the right. Now on Earth, objects have a very specific acceleration. That's negative 9.8 meters per second squared. So anytime something is in free fall, you actually know the acceleration. The acceleration, negative 9.8 meters per second squared. And that negative sign, once again, only represents the direction of the acceleration, which is downwards. Now, this acceleration due to gravity is only true as long as we're ignoring air resistance. And that's one caveat that a lot of people seem to struggle with, because we know air plays a role in how objects fall. But if we were to remove all the air, everything would fall at the same rate, which is negative 9.8 meters per second. So if there were no air resistance, all objects would actually fall at the same rate. Doesn't matter the shape, doesn't matter the size, doesn't matter how heavy it is. You could drop a hammer and a feather, and they would both hit the ground at the same time if you were to remove air resistance. But we don't actually see that in our everyday lives because we have air resistance all around us. Now, when an object is falling, its speed is increasing. Keep that in mind. Its speed is increasing, but its acceleration is staying constant. It's not increasing its acceleration. It is only increasing its speed. So what would motion graphs look like with an object that's in free fall? And we're going to use the example of something being thrown up in the air and then falling back down. What would these different graphs look like for that particular situation? So on the left, we got a position versus time graph. And this is what a position versus time graph would look like for an object that was thrown in the air and then fell back to the ground. So you notice the first part over here, it's going upwards, and the second part over here, it's going downwards. So you notice the position, and we're using the ground is 0, and its position is increasing, 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 and then it comes to a point to where it's not increasing its position anymore, and its position starts decreasing, and that's when it's falling back down to the ground. You notice that line is curved. You notice it's constantly curving downwards. That curve that's going downwards shows a negative acceleration. In our previous example, we had a curve going upwards, which showed positive. Here the curve is going downwards, showing negative acceleration, and that negative acceleration would be negative 9.8 meters per second squared. Now let's look at a velocity versus time graph and see what that would look like for an object being thrown up in the air and then falling back down. So you notice whenever something is thrown up in the air, it has a very high positive velocity initially, but then it's going to start slowing down. So in the process of it going up in the air, it has a high velocity, but it's approaching that 0 meters per second velocity. So it's going up, but it's slowing down. And then the second half is whenever it starts to fall down. So it goes up, it hits that 0 meters per second at the highest point, and then it's going to start to fall back down again. And you notice that it's got a constant negative velocity the whole time. Now let's look at what this would look like on an acceleration versus time graph. It would just be a flat line on the negative side of the graph on an acceleration versus time graph. So you see the first part is whenever the object is going upwards, and then the second part is when it's going downwards. We don't see a very clear moment whenever it starts to fall downwards, which is another limitation on acceleration versus time graph, but we notice that there's a constant negative acceleration the entire time. And one thing that is true on all of these graphs, at all points, if an object is in free fall, the acceleration due to gravity will always be the same. Its acceleration is not changing, it's staying constant in each one of these situations. Although the position is changing, although the velocity is changing, the acceleration is not changing. Thanks for sticking around. I hope this was helpful to you. If it was, make sure to hit that like button. If you want to see more videos, make sure to hit subscribe. And make sure to check out the links in the description below for more helpful information. Thanks, have a good day.